this is a real great honor for me, and I'm very grateful to Dr. Davis for organizing these meetings, and also for all the speakers that have spoken and will speak. And I'm was very pleased and moved actually by Dr. Bloch's describing the good old days at the Kaiser Wilhelm Institute, and I enjoyed his talk tremendously. I thought I would say or talk about something very similar, but he did everything so wonderful that I only have very, very little to add. And I think most will be sort of personal, but it might be of interest to you. This para-hydrogen story is like a detective story. The clue was that I think it was mentioned that Eucken in 1912 observed that the specific heat of hydrogen at around 100 Kelvin, which is about about liquid air temperature or thereabouts, it starts to drop off very precipitously, and it shouldn't do that. Why does it do it? It is a diatomic gas, and it should have the specific heat should stay at 5 calories and shouldn't drop down to 3. The other problem that bothered the scientists was that certain lines in the molecular spectrum of hydrogen had alternating intensity. There was a strong line and a weak line, and a strong line and a weak line. Now, why was that? And nobody could explain it. Then in 1927, suddenly there was a revolution in quantum theory. De Broglie, a French scientist, Schrödinger from Austria, Heisenberg and Dirac, almost independently developed a new quantum theory which is based on the wave nature of electrons and even molecules and the interaction of the atoms. And this was sort of a revolution. Many people didn't understand it. The situation was much worse with the new quantum theory than it was with the first time when the quantum theory of Planck was announced in 1900. That wasn't accepted too well till Einstein showed that it's applicable in the photoemission, photoelectric effect of metals, and when Niels Bohr explained the theory, explained the atom structure on the basis of the Planck's quantum theory. Well, Heisenberg pronounced that Heisenberg and Hund said that according to the quantum theory, there is a rule according to which the rotational numbers of hydrogen must be or even if the spin of the atoms are anti-parallel, and odd if the spins are parallel. Now this was almost unbelievable. What has the rotational quantum number got to do with the spin? Who knows whether even that is true? And then the consequence of this idea was that there should be a two system in hydrogen. the even quantum number system and the odd quantum number system. There shouldn't be transition between the two. Now, how could you prove that? Then Denison had the brilliant idea to do the calculation, calculate the specific heat of each of these modifications and see what he can do with it. And lo and behold, the figures that he got for the ortho modification and the para, if they combine that in the proper proportion, which is 3:1, was exactly what Eichen got for his specific heat in 1912, showing that there is indeed no interaction. Now the race to prove that there are two modifications was on. The first test was by McLennan and Lowe. They checked by Raman spectroscopy when you cool hydrogen down to near liquid or zero, liquid hydrogen is good enough. Then there should, if there is interconversion between even and odd numbers, then all the molecules should be in the zero rotation state. But the spectrum showed that about 3 times as many were in the number 1 than in the 0. So this was one good clue. The next clue was, or rather test was by Gio, professor of physical chemistry in California. He took liquid hydrogen, or rather hydrogen, and cooled it for several months, and then determined, pulled it down to the triple point, which is around, I remember, 4 or 5, something like that, and compared the two hydrogens, the fresh hydrogen and the old hydrogen. And he found a very small difference, about less than a millimeter mercury difference. Both were around 53. Now, this was, and he couldn't decide what to make of that, and couldn't say whether there was, the change was real or not. That was a very unfortunate test, as it turned out later, because there is a difference between the vapor pressures of ortho and para hydrogen at a given temperature, but he measured it at the triple point. And if you measure it at the triple point, then you have to take into account that the two triple points are not the same. And as it happened, that small pressure difference that para hydrogen would show, or that at least partially convert, would show, disappears because he measured it at the triple point, which is lower for para than for ortho. So that was unsuccessful. But now, this is an interesting story that Dr. Bloch mentioned about Eucken, that they may have started at the same time as Bonhoeffer and Hartek, or maybe Bonhoeffer and Hartek sent in the paper to the Naturwissenschaften, and Eucken said, hey, here is something that we should do it. Let's get busy and test this out and put some hydrogen on the test, and let's keep it for a few weeks and see what happens. But what makes me suspicious is this, that one test of Eucken is after 6 days, and the other is after 12 3/4 days. And I see that he probably told his assistant, look, there is the test, we can't wait another 6 hours because the deadline for the Naturwissenschaften is coming. You better test it right away. And that's how he got one after 6 days and after 12 and after 3/4. But anyway, I think he deserves a certain amount of credit because he did some wonderful work. Now, I think where Bonhoeffer and Hartek excelled is, you can call it luck or insight or intuition or brilliance or whatever, but they did it. First of all, they didn't use the old-fashioned way to measure heat capacity, because when you measure the heat capacity of hydrogen, you have a minute amount of matter versus a tremendous amount of weight in the gas cylinder and the other contraption, the water bath, etc. So your accuracy must be tremendously high, and the measurement is very complicated. Bonhoeffer and Hartek said simply this: from gas theory or physics, we know that the heat conductivity is proportional to the specific heat. So all we have to do is measure the heat conductivity, and nothing is more simpler than to measure the heat conductivity of a gas. If you have a filament, a thin filament supplied with electric current, and then the heat conductivity takes the current away, and the temperature difference between the wall of the vessel and the filament, which is very easily determined from its resistance, will do the trick. And that's what they did. Now, the first set of experiments were that they had these little cells. By the way, the wire was 1/100th of a millimeter. It's really very thin, but luckily it's supplied in this wire was supplied in a silver coating, which was much thicker than the inside. And when you handled it, you handled the thick wire, and all you have to do is dissolve the silver, and then the fine platinum wire was left behind. And this is the vessel they used. They used in the vessel low pressure, around 40 millimeters, to avoid what happens in heat, convection. They didn't want to have any convection, just heat lost by heat conductivity, and that's why you have to use low pressure. If they had used higher pressure, there would be convection, and you get another effect in addition to heat conductivity. So these experiments were unsuccessful, and as it turned out, they had to decide that there is no interconversion between the even and odd states within 1 year or thereabouts, which was a fairly good estimation of the theoretical physicists, who estimated that the transition time would be from 300 years down to about 1 or 2, something like that. But then they must have had real luck with the charcoal, because nobody would think that would be a catalyst, and certainly not at the low temperature they were. But later it turned out that everything fitted together, because this was some kind of a magnetic or effect which is connected, which causes the conversion either by the vicinity of other molecules which have magnetism, or some magnetism of the residual valences of the charcoal. Subsequently, we at Frankfurt made very elaborate tests on various charcoals, including very, very pure charcoal prepared from sugar. And this by the sugar, so to make it recrystallize from alcohol several times, and then eventually the sugar was cooked and converted into charcoal. By the way, at that time, this work had a very important side product. You see, during recrystallization, the sugar from alcohol, you had to use very pure alcohol. There was a lot of alcohol left with a little sugar in it. So we found good use for that in some non-chemical way. But it turned out that any charcoal will do it, and later it was found that the oxygen, molecular oxygen, pre-adsorbed on charcoal enhances the effect. Now, Dr. Bloch mentioned this effect. This is the effect that my brother and his assistant or collaborator, Dr. Sachs, found. And this is an interesting story. Now, why did they mix hydrogen with oxygen? Normally, you don't do that, right? But they did it on purpose because they were interested in ignition. This was one important field that was worked on in those days because of the rapidity of the combustion and explosion and that sort of thing. And they suspected that the reaction is connected with or initiated with radicals, hydrogen radicals or OH radicals. So the idea was, if you have the explosion limits or combustion velocity of hydrogen and oxygen, this is well known. Now what if you use para-hydrogen? So I think it wasn't a very brilliant experiment, but I think somebody, the boss wanted it, so they did it. So they mixed hydrogen and oxygen. And every time they tested the data, exactly the same result came out with para-hydrogen as with ordinary hydrogen. Now, everybody would have given up at this point. But then my brother said, why don't we check the para-hydrogen? Well, it's easier said than done. In order to check the para-hydrogen with the heat conductivity method, you have to remove the oxygen. So they had to remove the oxygen by freezing it out with liquid hydrogen. And they tested, and lo and behold, the para-hydrogen was converted into ordinary hydrogen. And they tried that several times, and they figured out why would oxygen do it? Nitrogen didn't do it. And they guessed it was magnetism, and then they tested a number of other paramagnetic gases like NO, NO2, and a number of ions, and they all worked, and Wegener then developed a theory, and the magnetic moment of the catalyst goes in, I think, at a higher power, and then they calculated that if you have two ortho molecules and they get together or hit each other, then the ortho molecule has a magnetic moment and can switch the other one. So it's really turned out to be that in liquid, where the molecules are very densely packed and solid, this is a bimolecular reaction, and it follows the bimolecular kinetic law, except in the case of solid, because in that case the molecules are packed, and if they say that in order to switch one ortho you need two ortho molecules, and then eventually in the liquid, in the solid, there are nothing but single ortho molecules, and they have nothing to switch them over, so then the rate slows down. This is what Polanyi showed. Now, maybe I should tell you how I got into this. While the great new quantum theory and quantum mechanics and wave mechanics was developed, I was a student of chemical engineering in Vienna, and I finished. I graduated in 1928. In the meantime, my brother, who was 2 years older, he went to the Charlottenburg Technical University. This was his dream ever since he was in junior high school. He studied relativity theory and vector analysis and God knows what. He was a real expert. But he started in 1922, and that was the worst year or beginning of that horrible inflation in Germany. But this wasn't the main problem. The problem was that they couldn't take him for the chemistry faculty, and they took him only on, I think, electrical engineering. And he didn't like that very much. He just studied for a year. And then he went to Vienna, where I joined him later. But before I was finished with my first year, they called him that there is room for him in Berlin, and he went right there, and he finished in 1926, I think. And then he took a PhD degree in engineering, chemical engineering. At that time, for some reason or other, there were a lot of Hungarian compatriots of ours and some very brilliant compatriots. Wigner was there, I think Teller and Szilard. Szilard was an assistant, Leo Szilard of the atomic bomb fame. And he, in fact, sort of sponsored my brother, and when he got his PhD degree, he recommended him, my brother, to Bonhoeffer or Haber. I think he had some contact with Haber for an assistantship. And my brother got to the Kaiser Wilhelm Institute around in 1927. And he and Bonhoeffer worked together. And when I graduated, he asked Bonhoeffer whether he would take me on as a graduate student. And Bonhoeffer asked how I'm doing in chemistry and math and so forth. So, of course, my brother gave him very good recommendation. And that's how I got there in 1928. And Bonhoeffer gave me a job or a thesis to work on the gold and silver hydrides, which were non-existent then. But the main thing was to pass hydrogen over these metals and see if you can get the Hg or AuH spectrum. And sure enough, you could get it, very faint lines at the proper line. And I did all I could. By the way, this was a tremendous oven, a graphite oven, which was heated by high copper bus, which were clamped on it, and passed about 2,000 amps through, and it heated by resistance heating. And this current was supplied by a tremendous generator, which I don't know when. You remember when this was not there? I think 20 horsepower or 200 was tremendous, because it provided enough power to illuminate a small city. But anyway, you had to turn that or crank it on, and sometimes, and then when you wanted to turn off, you crank it down. And somebody who used it before me, I'm sure, didn't crank it down, and I turned on the big switch, and there was a tremendous explosion, and the whole institute lost the power, and they almost lynched me, and I don't know, what am I doing here? But it was repaired in due course, and I finished this work. But when I practically witnessed this discovery of para-hydrogen, because in the last days they knew that something was coming, because they already observed the low pressure conductivity work didn't show anything. But then they also measured with the conductivity method liquid hydrogen that was a day old or 2 days old, and they found that for every hour it practically increased by a few percent, not a 0.5%. So liquid hydrogen that stood around for a day maybe had, instead of 25% para, maybe 35 or something like that. So the effect was already known. But then they tried this charcoal catalysis, and that, of course, just like that did it. And then in practically 1 day they did all the tests you could think of. They did it in liquid hydrogen and made pure para-hydrogen, measured the vapor pressure, boiling point, melting point, everything, various other physical properties. And there was hardly anything to do. Then I told Bonhoeffer, couldn't I would like to do something, some catalytic work or whatever. So he said, why don't you try the thermal conversion? And that's when I did this work, which turned out really good. And I want to tell you a little personal story. When I found this connection, the 1.5 power for the pressure, 1.5 order, and first order for the progress of the reaction, there was a young graduate student at Polanyi's lab. I saw him in the laboratory, and I wasn't speaking to him. And I said, Henry, his name was Henry Eyring. And I said, look, this is what he said, you know, I'm working on this very same reaction, and you did it. And this was the big surprise for me. And of course, I was very pleased. And then in 1930, I went with Bonhoeffer to the... Is my time up?
You still got 5 or 10 minutes.
Enough?
No, keep going.
Well, just one more. And then we started on the catalytic work, which was also very successful. And then I had a big luck, because there was a big meeting of the Paradise Society and in London, or rather in Oxford in 1932, about absorption. And Bonhoeffer was supposed to present our data on the catalytic conversion. He said, I don't know why he didn't want to go. And he said, why don't you go? And I went, and that was a big deal for me. They treated me by a VIP and entertained us. And the lecture was a big success, and Professor Riedel practically commissioned me to write a book on ortho-para hydrogen. And a few years later, actually a year later, I had to leave the Kaiser Wilhelm Institute because of Hitler, and I got a place at Professor Riedel's laboratory, so everything turned out good. So I think I'll stop at this.